I worked out how to use my accordion as a wireless game controller, and I want to show you how I did it. Here's the basic steps. I found PAC-MAN code for Python online. I trained a basic AI model to listen to the microphone and detect which accordion note I'm playing. I found the spot in the PAC-MAN code controlling PAC-MAN's direction, and I modified it to use the AI model instead of cursor keys. I wanted to do this in Python to simplify the number crunching, but I didn't really want to write a whole PAC-MAN game from scratch. So I had a look around and I found a site called PACMANcode.com. It's a series of game programming tutorials. Looks really well set up. I'm afraid I didn't actually work through any of it. I simply downloaded the final version of the code. I can't actually see who wrote this, but thank you, whoever you are. Anyway, it relies on Pygame, which is a popular game programming package for Python. So I downloaded and installed that as well. And after unzipping the PACMANcode.com package, I just go into the new folder and type python run.py and starts a PAC-MAN game. And you can begin it with the spacebar and play with the cursor keys. And I'm not much of a gamer really, but anyway, that's the way any sane person would play it, right? Just control PAC-MAN with the cursor keys and then, Algorithmic pitch detection is a surprisingly hard problem in general, but I had a huge advantage here because I knew the instrument I was using, and the microphone, and even the room. So I thought a simple method stood a good chance. So I made a 30-second sample of each of the notes on this keyboard. Within each sample I tried to play at a range of volumes, and to include a lot of back and forth on the bellows, so the AI could learn all the different ways each note could sound. For the AI, I used PyTorch, a popular Python package for working with neural networks. Neural networks can be very complex and powerful and require a lot of computer time to train, but I only needed a simple neural net, and mine trained in about 20 minutes without any GPU acceleration. And that's because, in this case, most of the work can be done by the fast Fourier transform. Okay, I'm suddenly saying a bunch of technical stuff, and I'm not sure who my audience is. So, to be brief, the fast Fourier transform, or FFT, is a very efficient method for inputting raw audio data and outputting the phase and amplitude of every frequency of sound within the signal. I think it's safe to ignore the phases. Our ears mostly don't hear phases anyway, so I rolled those up to get just the amplitude of each frequency, and then I fed this graph into the neural net. I'm recording at the standard CD sample rate of 44,100 Hz, and I'm using audio chunks of 2048 samples, so that means that about 22 times a second, it's going to listen to an audio chunk, classify it as one of the notes on the keyboard, and then use that to control PAC-MAN's direction. I'm using 2048 because the FFT likes powers of 2, and that's going to give us 1024 different frequency amplitudes. The idea is that these frequency amplitudes should somehow tell us which note the accordion's playing. Let's zoom in a bit. This audio chunk is from a B flat, which is nominally 233 Hz. If the accordion emitted pure sine waves, then I could just check this frequency. That might even work on like a flute or a theremin, but accordions make a very harmonically rich sound, so there are all these other frequencies appearing called overtones. Now a lot of these overtones could just as easily indicate different notes. For instance, this is the fundamental frequency in overtones for a B flat 1 octave higher. Lots of overlap. Here's the overtone series for a B flat 1 octave lower. Again, lots of overlap. So it looks like detecting which octave I'm playing might be quite hard. And it's actually especially hard on the accordion. I'm using the so-called master switch here, which means that each note is actually using reads from 2 different octaves. So when I play this B flat and then this B flat, there's one read that they're both using. So the AI might struggle with that sometimes. Anyway, here's a note that's not a B flat at all, and we still see a considerable overlap. Of course, F and B flat are close harmonically. They're right next to each other on the circle of fifths, so maybe this isn't surprising. A is not harmonically close to B flat, so we don't see any exact matches, but it is close chromatically. And now we notice another problem, which is that these peaks aren't really very narrow. For these first three peaks, they're likely to give us a false positive for A if we're not careful. Well, why are these peaks this wide anyway? We could resolve the sound more accurately and compute narrower peaks, but to do that we'd need to use larger chunks of audio data, and that would create a perceptible lag when I try to use it as a gain controller. So it's kind of a compromise, but it turns out that this is good enough. By looking at all of this frequency data, the computer can pretty accurately determine which note I'm playing. I'll just quickly mention that this trade-off between accuracy and responsiveness is really pretty similar to the famous Heisenberg uncertainty principle from quantum physics. Heisenberg says that you can only make the position of a particle definite by making its momentum less definite, and vice versa. And it comes down to the same reason. There's a Fourier relationship between a particle's position and momentum. But let's not get sidetracked. The point is, frequency detection is kind of complicated. I should identify a collection of frequencies I expect to hear, and another collection of frequencies I expect not to hear, and then I should see which frequencies are present and make a judgment call. Except that all sounds like a giant hassle, so I got the AI to do it instead. I trained the model, which means the computer calculated which frequencies it expects to be present and absent in each note. That takes a little while, but then during gameplay I'm only applying the pre-trained model, so it can very quickly apply the FFT, see which frequencies are present, and then guess which note it is. The neural network looks like this. The inputs to the neural network are the frequency amplitudes, and the outputs are a node for each of the 34 accordion keys. I don't need any middle layers because the FFT is doing exactly the sort of convolution that you might typically expect to see in middle layers. And in fact, the only nonlinearity here is the so-called softmax at the end, which is only used when training the model. So this is why I keep calling it AI with quotes, because it's really just a glorified linear classifier and I'm barely scratching the surface of what neural networks can do. But PyTorch was a quick practical solution because it's an easy way to design and train and apply a classifier. Actually, this is the second method I tried, and it was easier and more effective than the first method. Anyway, let's try it out. Before connecting it to the PAC-MAN game, we'll take a quick look at pitch detection directly. So, pretty good. Okay, what's going on here? That's pretty good. That one's a bit fishy, right? It's having a hard time, well, it's worse when I'm talking, but it's having a hard time determining which octaves this note is in, right? Okay, so mostly pretty good. It's not flawlessly distinguishing all 34 notes on the keyboard, but we're not trying to play 17-dimensional Pac-Man. Pac-Man can only move in 4 directions, so we really just need to pick 4 notes on the keyboard that it can always tell apart. I thought a natural choice would be these 4 notes. Because for one thing, I can easily reach them all without having to move my hand around, but also, they don't have much overlap in their harmonic series. They're equally spaced around the chromatic circle, or if you only have room in your heart for one music theory circle, they're also equally spaced around the circle of fifths. I don't know whether this was necessary, but I retrained the AI model to have only 4 output nodes, so that is to just try to detect these 4 notes and not worry about the other 30. I didn't have to change very much in the code. The biggest change was to add this mic listener class, and it, firstly has a copy of the neural network class that was defined in the training code, and when the mic listener object starts up, it instantiates the neural network and loads the dictionary that was saved by the training code. And then it also turns on the microphone in this Pi audio code. And then every time the heard method is called, it listens to the last audio chunk and uses the neural network to classify it, and then returns its estimate of which note is being played on the accordion. And then in the PAC-MAN object class, I just replaced the content of this getValidKey method, which used to interrogate the this kind of keyboard, with an index into self-controls mapper. So this is what's coming back from the mic listener class, the estimate of which note I'm playing, and then I'm using a controls mapper to actually map that to a direction. The main reason I did that is because I wasn't too sure. I was a little indecisive about which note was going to be which direction. So I tried out 3 choices, and I think I have decided I prefer to go with the sort of Vim-like key mapping. All right, let's try it. I'm not much of a gamer, so this is certain to be a ludicrous display, as they say in the IT world. I should just mention, in the original version from PAC-MAN you're supposed to press the space bar to start each round, and that's a little awkward from behind the accordion, so I've made it noise activated instead. So I'm just going to run the code and then very quietly play the game. Okay, I hope you enjoyed hearing about that, and I'd be thrilled if anyone wanted to take it further. I'll put a GitHub link to all the code in the video description, although of course the majority of the code is just from pacmancode.com, so I hope they don't mind. But I'm also providing the code I used to train the AI model, and even a basic utility to create the audio samples in the first place to use as training data. So the simplest thing you can try is just to train your own AI model, assuming you don't have an accordion, so that it can recognize the notes from your, kazoo or harp or whatever you've got, and then you can play Pac-Man yourself using that. But I was also thinking, the 4 notes that I'm using to control Pac-Man, I had reasons for choosing them, but they don't sound particularly nice together. And it would be amazing if someone were able to actually play Pac-Man and, beat the level and sound musical while they're doing it. And, the pitch detection code was pretty accurate. Mostly it only mixed up notes that were an octave apart when I, tested it on all 32 notes. And so what we could do, instead of assigning 1 note to each of the 4 directions, we could assign a chord to each direction. And as long as, you play any note from that chord, then then Pac-Man will move in the direction you mean. And that way, you can just noodle along in 1 chord, as long as you want to move 1 direction, and then just change chord to turn a corner. So, that might be fun if you're good at improvising. How would we choose the 4 chords? Well, the obvious choice is symmetrical. Just use the 4 augmented chords. That probably wouldn't sound a whole lot more musical. But there are other choices that might have more aesthetic potential, like these four: D flat, E flat minor, G, and A minor. I think actually beating a Pac-Man level while also sounding musical would be a very neat trick, and if you can do that, I'd love to see it. Alright, if you have any questions about this, or if you want to try something similar and you get stuck, ask a question in the comments and I'll try to help. Thanks for watching.